Good day, class. In this video, I will discuss the importance of forward kinematics. Okay, so forward kinematics is the geometrical problem of computing the position vector and orientation of the end effector given the joint variables. So after the parametric table, okay, after constructing and filling out the parametric table or doing the long method, which is the deriving the rotation matrix and the position vector for the mechanical manipulator, so you will have what we call the homogeneous transformation matrix. So either of the method you use, you will still arrive at the construction or forming of the homogeneous transformation matrix. Okay, so if you already have the homogeneous transformation matrix from either method, okay, so what you will do is you may now substitute the value of the joint variables and the value of the link lengths. Okay, so for example, for this problem in this drawing, okay, so we have here the kinematic diagram of a 2 degrees of freedom spatial mechanical manipulator. Okay, so the problem is find the position and direction of the spray at the end effector. So we have here the spray at the end effector where there are given joint variables. So theta 1 is equals to 90 degrees and theta 2 is equals to negative 90 degrees. While the link lengths are all 3 units. So let's just give them 3 units. Okay, so after getting also the homogeneous transformation matrix, okay, so to answer this, you will just substitute, okay, the values of the joint variables and the link lengths in our homogeneous transformation matrix. Okay, so let me use my calculator. Okay, so because we already have the homogeneous transformation matrix, we can use the calculator, okay, to get the position and the direction of the spray at the end effector. Okay, so to get first the direction, okay, the position of the spray, okay, we will substitute the values of the joint variable and link lengths to our position vector, okay, to the column of our position vector. So this is the column of the position vector. So this is the position vector. This is what we need first to answer, okay, using calculator. Okay, so we have here A2, so all our link lengths are 3 times cosine theta. Cosine T1 is 90 degrees, so cosine 90 plus A4, so 3 again, times cosine T1, so cosine 90 again, times cosine T2, which is negative 90 degrees. Okay, minus 3 times sine 90 degrees, sine T1, times sine T2. Okay, so T2 is negative 90 degrees. So the answer is 3. Okay, the answer is 3. So let's put it here. The answer is 3. Okay, so the first row for our position vector, or the first element for our position vector, is for the x coordinate or the x element. So next is the y element or the y coordinate. Okay, so to make this computation faster, let's find out what is sine t1 or cosine t1 or cosine t2 or sine t2 first. So if you have 0, okay, we can cancel other expression. So if you have answer, we have if you have 0 answers, we can cancel the expression fast. Okay, so a2, so sine 90 is 1. Okay, cosine 90 is equals to 0. So this expression is already cancelled because cosine 90 is 0. So everything you multiply to 0 is 0. So sine 90 is 1. So if 82 is 3, we will have 3 times 1. Okay. So cosine t2, cosine negative 90, cosine negative 90 is equals, oh, this is also 0. Okay. So this is cancelled. So we will have here 3 times 1. So y is equals to 3. Okay. Oh, sorry. So y is equals to 3. Next, for our uh, last element of our position vector. So this is 3 plus 3 is equals to 6. So a1 plus a3 is equals to 6. So this equals to 6. Okay. So this is your position vector. Okay. Your values for the x, y, and z coordinate, okay, are your position vector. Okay, so what does this telling us is the end effector will position at x is equals to 3 units, y is equals to 3 units, and z is equals to 3 units. So using a three-dimensional table, okay, it should look like this. Okay, so if we manually search where is 336 in our three-dimensional Cartesian coordinate system, okay, it will be look like this. Okay, so at this position, the spray, okay, the spray will be found, okay, using the given joint variables, okay, theta 1 and theta 2. So it's 336. Okay, so how about the direction? So the direction will be based on our rotation matrix. Okay, so if we remember, okay, the columns of our rotation matrix uh, stands for the projected matrix, uh, projected frame. Okay, it represents the projected frame. The columns of our rotation matrix. The projected frame is the end effector frame. Okay, so This is the x2 or x, sorry, this is the x02. This is the y02. Okay. And the last one, this is the z02. Okay. So let's put some label. Let's put some label. Okay. So x. So the column represent the column of the columns of the rotation matrix represents the reference frame. Okay, so the reference frame consists of x sub 2, y sub 2, and z sub 2 because the reference frame is the end effector frame. Okay, so these are what uh, the columns represent. So if we put in a vector each column, okay, it would be look like this. Okay, for z sub 2, so let's move this table to the other side. Okay, if we put the z sub 2 column in a vector, okay, so it shows that the projection of z sub 2 to x sub 0, y sub 0, and z sub 0, because uh, our projected frame is the base frame, which is the frame 0. Okay, so z sub 2 is projected only to z sub 0. Okay, so to find also the projection of y sub 2 to x sub 0, y sub 0, or z sub 0, we will just substitute the joint variables. So T1 is 90 degrees, T2 is negative 90 degrees. So cosine T1 or cosine 90 is equals to 0. So this will be cancelled. This will be cancelled. So cosine negative 90, let's see. Cosine negative 90 again is also 0. So this is already cancelled. So this is already 0. 0 minus 0. Then cosine 90 is 0. While sine T1 is 1. Right? Sine 90 is equals to 1. Okay. Sine negative 90 is equals to negative 1. So 1 times negative 1 is negative 1, but this will become 0. Okay, this will become 0, so 0 minus negative 1. Okay, so because this is a minus negative 1, it will become a plus. Okay, 0 plus 1, so we will have here plus 1 or positive 1 for the y sub 0 column. Okay, then the last column is 0. So if we put that in a vector, the column of y sub 2 will look like this. So y sub 2 is only projected at y sub 0. Next, for x sub 2, okay, again, we will substitute the joint variables. So cosine 90 is 0. So this is 0. So sine, so we have here Sin T1 is 1, sin T2 is negative 1. Again, 0 minus negative 1 is positive 1. Okay, next. So cosine 90 is 0. Cosine 90 again is 0. So 0 plus 0 is 0. So if we put it in a vector, the x column will be look like this. Okay. So these are your values from your homogeneous transformation matrix. So the position vector is already plotted, okay, in our table, this table. So how will you plot the the rotation matrix or the vector form of the x sub 2, y sub 2, and z sub 2 at this table? Okay, so if you remember, class, let's go back to the original drawing. Okay, from the lecture of rotation matrix, every line, okay, every arrow or every axis is equivalent to 1 unit. Okay, is equivalent to 1 unit. So to plot these vectors or the rotation matrix in our table, okay, so we will start at x sub 2, okay, projected only at x sub 0. So this is x sub 0, okay, this is x sub 0. We will add we will add 1 to the position at x axis, okay. So 3 plus 1 is equals to 4. Okay. Then uh, we will look we will plot the direction x, okay, using a line. Okay. So it will look like this, okay. Then from there, so this is the intersection, okay, from the added from the plus 1 unit, okay, and the 3 units because of the value of y at the position vector. So from there we will draw upward another line, okay. Okay. So from that, from the point of the position vector, we will draw an arrow, okay, up to the drawn arrow, okay, from the intersection of the added 1 unit because of the direction at x-axis, okay, to show the direction of this spray at the along x-axis. Okay, so this is the x sub 2. Okay, this is the x sub 2. Next, let's go to z sub 2. Okay, so z sub 2 is only projected at save sub 0. So what does that mean is we will add another unit, okay, after the position, okay, position of position at z-axis, okay. So from this added unit, we will also draw another line. Okay, we will use the axis. We will use the axis of the y sub 0 as reference. Okay. Then through this added line, we will draw we will draw the arrow of z sub 2. Okay. So this will represent the z sub 2. Okay. So this is like plotting the frame 2. Okay, we are plotting the frame 2 using the values using the derived values from our transformation matrix. Okay. So we have now the direction of x sub 2 and z sub 2. So for y-axis, we can use the right hand rule. Okay. So z sub 2 is pointing upward. So this is the thumb. X sub 2 is the four fingers. The direction of the palm. The direction of the palm is backward. So y sub 2 will point backward. Okay. So this is y sub 2. Okay. So this plot shows the position and direction of the spray at the end effector. Okay. So if you notice, okay, uh, it is not that presentable if we are plotting it in this kind of plot. That's why we are using that's why we are using simulators like MATLAB. So if we plot it in MATLAB, okay, using the robotics toolbox by Peter Corke, okay, it will be more presentable. Okay. So while waiting, okay. So this is the code for the uh for the simulation of the mechanical manipulator using the robotics toolbox by Peter Corke for MATLAB. So if we run this, okay. Oh, sorry, this is not the program. Okay, this is the program, sorry. Okay, F5. Okay. It's not yet. Oh, there is an error. I have here an error. Sorry. So let's fix the error. So the error is it does not recognize the the link variable. So this is not a variable. This is the command. Okay. So to run this, you need to find the folder. Sorry, the application RTB where our robotics toolbox application is located. So what we will do is we will open this rtb.mltbx. Okay. Then we will run this. Okay. So it's installing. There sometimes it does not it does not install automatically. So we need to install it again so that it will recognize the commands. Okay. So let's use CLC. Then run the program. Okay, let's see if there's okay, it's running now. Let's wait. So this is our 2 degrees of freedom manipulator. Okay, so let's adjust a bit so that it could be bigger. Let's adjust it in our workspace. So 0, 10. Let's make this -5 at the x-axis. Okay. So again, let's close this. Let's clear all. And CLC. Okay. Then F5. Okay. So it's much bigger. Okay. So we can see or we can interpret here clearly the values of our joint variables by just putting or sliding our slide switches into 90 degrees and negative 90 degrees. Okay. So this is how our mechanical manipulator will look like if the joint variable is 90 degrees and negative 90 degrees. Okay. This is also the position. Okay. 3, 3, 6. So this is what it will be look like. Okay, so how about our forward kinematics? So our forward kinematics is not yet coded in this program. Okay, so what we do in robotics toolbox, okay, we have here what we call the fkin command. Okay, so let's put the fkin command under our kinematic diagram simulation program or codes. So this is uh, forward kinematics. Let's name this section forward kinematics. Okay, so I have already here a value of QF. Okay, or let's name it FK. Okay, a small letter FK. Okay, so FK is the value of the joint variables. Okay, so our joint variables, let's start from 0. Okay, let's start the joint variables at 0. Next. Okay, so this one is, let's name it F, capital FK. Okay, so so let's see. Let's make this F key and this one is F key. Oh, it's the same. It's just capital letter. So let's put some. Let's put some this one. Then underscore. Okay. Then the syntax is the name of our mechanical manipulator. The name of our mechanical manipulator, I've given it the name as underscore 2df. Okay. Then the command dot fkin, close open parenthesis. So inside of it is the fkin. Okay, the variable fkin. So the fkin variable again holds the joint variable 0. Okay, while fkin variable holds the command of the fkin okay, Fkine or Fkine, okay, to compute the forward kinematics. So let's clear all. Then CLC. Okay, let's close our simulator. So we have here first the forward kinematics if the joint variables are all zero. Okay, sorry, where is it? Okay. If all the joint variables are zero. If we want our joint variables to become 90 or 90 degrees, let's make another fkin variable. Let's give it an fkin underscore 1. Name is equals to square parenthesis. So the default unit in any programming language is radian, so let's give it a pi over 2 and negative pi over 2. Okay, joint variables. Next, so f underscore kin underscore 1 is equals to s underscore 2 dof dot fkin. The fkin and inside the close open parenthesis is the variable fkin. So if we run this, so we have here again our simulator. Okay, and at our inside our command window, okay, we will see here first the X parametric table, okay, by the robotics toolbox, the homogeneous transformation matrix created by the command of fkin, where the variable is fkin that holds the joint variable 0 and 0. Okay, so these are the joint variables theta 1 and theta 2, 0 and 0. Okay, next, okay, fkin 1 holds the, sorry, fkin 1, okay, gave us uh the value if the homogeneous transformation matrix if the if the joint variables are 90 degrees and negative 90 degrees. Sorry, this should be fkin underscore 1. Okay, so this is wrong. Again, clear all, CLC. Okay, so let's run again, F5. So this should be fkin underscore 1. Okay, so that the joint variables that will run by the fkin command is pi over 2 and negative pi over 2. Okay, so F5. Okay. So our command window. So this is the 0 degrees, both 0 degrees for theta 1 and theta 2. Okay, so the joint variable is 606. Oh, sorry, the position vector is 606, the same with the end effector coordinate here at our simulator. Okay, the same also with the value of our Q1 and Q2 here, our joint variables. Okay, a minute. Store, sorry. Okay, I'm just fixing the size. Oh, it's not getting better. Okay, again. Clear all. CLC. Okay. So let's run this again. Oh, it's wrong. Wrong. Sorry. Wrong code. Okay, so this is what we want. Okay. So it's not yet. Okay. It's better. So the command window, at the command window, okay, this is the homogeneous transformation matrix. If both the joint variables are 0, okay, the position vector is 6, 0, 6. The same with the coordinates here. If the joint variables at our sliding switches are 0. Okay, so this one, the fkin underscore 1, this is its homogeneous transformation matrix. The position vector is 336, and this is the rotation matrix. The same with our uh, computation. Okay, so this is a rotation matrix. This is the position vector 336. Okay, so if we change this to 90 degrees and this one to negative 90 degrees, okay, the coordinates for our end effector is also 336. Okay, so this is the reason why we are using the robotics toolbox, okay, to show if our calculations are correct. Okay, this is also proof that our doing can design a robot manipulator, okay, or a mechanical manipulator. Okay, so further details about the use of this general matrix formula, okay, because we are just using the codes of robotics toolbox. Okay, the the codes of the robotics toolbox is different from the real derivation or real coding of this general matrix formula in our programming language. So I will further explain this, okay, at robotics 2. Okay, so we will use both MATLAB and Python to further explain the detailed coding of this general formula of our homogeneous transformation matrix. But for now, okay, so this simulation proves that our calculations are correct, and it proves that what we are doing can design a mechanical manipulator. Okay, so after this is the inverse kinematics. Okay, so it will be on our next video.